First-order differential equations track single rates of change. Solving second-order linear equations requires a different approach, modeling entire structural systems. The second midterm in this sequence evaluates your grasp of one unified concept, rather than a loose collection of calculation tricks. That concept is the behavior of second-order linear systems, where every response is strictly proportional to its stimulus. This is the generic mathematical form for these systems: y double prime plus p of t y prime plus q of t y equals g of t. Extracting a solution from this structure requires dismantling it. We must solve the two halves separately, isolating the left side from the right. This mathematical split mirrors a physical reality. We isolate the system itself before considering the outside forces acting upon it. The principle of superposition governs this separation. It dictates that the general solution is the addition of two pieces: the natural, unforced behavior, YH, and the forced, steady-state behavior, YP. In this 2019 exam question, we see the split. The blue left side is our system. The orange right side is external forcing. We set the system to 0, converting it to a characteristic polynomial. Lambda squared minus 1 equals 0 yields roots at 1 and -1. These roots define the homogeneous solution, the system's transient state. This is the inherent motion the system exhibits when isolated from the rest of the universe. The homogeneous solution serves as the system's mechanical DNA. We establish the spaceline before introducing the complexity of the external forcing function, g of t. These abstract characteristic polynomials perfectly mirror the behavior of physical objects, like this industrial spring compressing under a steel block. Applying Newton's second law to a mass spring damper system yields the same structural polynomial. Equation 4u double prime plus 8u prime plus 40u corresponds to mass 4, damping 8, and stiffness 40. The -576 discriminant pushes the roots into the complex plane. This underdamped system means the mass undergoes a sinusoidal oscillation, exponentially decaying back to equilibrium. If damping is removed entirely, as seen in the 2018 exams, the roots sit purely on the imaginary axis. Without a real component to drive decay, the oscillation never stops. The coordinates of these roots in the complex plane dictate exactly how the physical object will move in the real world. We now return to the external forcing function, g of t, the orange half of our master equation. The method of undetermined coefficients requires us to guess the shape of the system's reaction based on the shape of the incoming force. A common hazard in the 2017 and 2018 midterms occurs when the external forcing frequency matches the system's natural frequency. Matching frequencies cause the waves to overlap, creating a mathematical conflict. The standard guess fails because it is not linearly independent. We resolve this by multiplying the guess by t to force independence. As t is introduced, the response wave's amplitude expands over time. This is resonance. The system's amplitude increases linearly until it reaches structural failure. Resonance occurs when an external force exploits the internal mechanics of the system, turning a stable model into a physical disaster. The tools used for constant coefficients rely on the assumption that parameters like mass and stiffness never change. In question 3 of the 2017 midterm, the coefficients are variables. The x components attached to these derivatives make standard exponential guesses impossible. To solve equations with variable coefficients, we assume the solution takes the form of an infinite polynomial, a power series. The mechanical challenge lies in summation alignment. We take derivatives of the series and shift the indices until the powers of x lock into perfect vertical alignment. This alignment allows us to define a recurrence relation, which generates the infinite chain of coefficients required for the solution. When the constants of reality fail, we map our unknown function into infinity, expanding it to approximate the truth. Discontinuous external forces, like a lightning strike or a sudden violent impact, present a final obstacle in these exams. Calculus requires smooth, continuous functions. When a function contains jumps or breaks, standard time-based derivatives fail. The Laplace transform provides a way to bypass these discontinuities. The Laplace transform projects the system into a domain shift. It moves the problem from the t domain, or time, into the complex frequency domain, S. This integral projection collapses a messy differential equation into a clean algebraic fraction. We then solve for y of s using algebra and apply the inverse transform to pull the answer back into the reality of time. These exams evaluate structural strategy, knowing when to guess, when to expand into infinity, and when to abandon time to solve the linear operator.